I think we can start. I think we crossed more than 220 participants this semester already. So let me start. Welcome to Data Science Seminar of 2023 fourth semester. This is the eighth seminar offering since the Graduate School of Data Science started in 2020 March. Today we have a speaker that is very difficult to get. The Gen AI and the ChatGPT has become a hot topic almost a year, and today we got Dr. Hyungwon Chung, who is a member of ChatGPT team at OpenAI. Let me introduce Dr. Chung a little bit, and then I'll ask him to spend more time I ask him to explain himself. So Dr. Chung received his PhD from MIT, I think in mechanical engineering, and then he transformed himself to become AI person, and he at Google Brain, and then I think he spent 4 years at Google Brain, and then moved to OpenAI in the beginning of this year. So he's actively, I think he knows all the details of our ChatGPT create language models. And today he's going to explain the process of creating LLM, and then and at each step, what are the issues and what kind of research problems to solve for the future. So with this introduction, I'll pass the microphone to Dr. Chung. It's all yours, Dr. Chung.
Thank you for the introduction. Can you hear me?
Yes.
Yes. Thanks for the introduction. So my name is Hyungwon, and today, let me just present it. Yeah, I will talk about large language models in 2023. Why do we need that suffix in 2023? What we call large is misleading in that large models of today will be small models only in a few years. Along with that change in the perception of scale, many insights, observations, and conclusions we make along the way with the current large language models will be outdated and in some cases invalidated. Fortunately, insights based on first principles or that are fundamental tend to stay relatively longer than the advanced ideas that look so fancy. In this talk, I would like to share such fundamental ideas that I have observed working in the field for the past 4 years, and mostly by observing some of the brightest minds that I'm fortunate to have interacted with. My hope is that whatever I talk about today is fundamental enough that it stays relevant at least for a few years. Let's get started. There's one unique aspect of large language models, and that is some abilities only emerge at certain scale. And this makes really important to just have a different perspective in viewing all this field. So here's what I mean. Details don't matter here. X-axis is some scale. You can think of it as a model parameter count, training data, training compute, whatever. You just think about some scale. Y-axis is also not that important. Some performance metrics of the task that you care about. And we have seen over and over this kind of pattern where small models just don't have any chance of solving it, 0% or random guessing. And at some scale, suddenly the model solves this task, and sometimes very well. And this kind of phenomenon, we call it an emergence, a phase change like sudden emergence of this capability. And this is very unique for this large language models. And I think this brings many important perspective change that for AI researchers. First one is this perspective of yet. So let's say we have this new idea that I want to test out. And let's say some kind of a new reasoning techniques, and I try out the experiment and say it doesn't work. Most of the time it doesn't work. Then instead of saying this doesn't work forever, I want to say this doesn't work yet. And this is really a fundamental change in the viewpoint. I'm saying this might not work for the current generation of the models, but in 3 years, 5 years, that might not work. That might just work. And so we should really not conclude many things that in a permanent sense. And if we think about why this perspective is not so obvious, we're so used to operating in an environment where the underlying axioms don't really change. So let's think about this, an experiment, an example where, let's say you run some physics experiment or you study thermodynamics, which I did, and then you run some experiments. And then if you have some new idea and this experiment doesn't work out, then you know that if you run it again 3 years later, this will not work. For that matter, 30 years later, this doesn't work. The underlying physics, second law of thermodynamics doesn't change. And we know this, and we're very used to this kind of situation. And a lot of the human experience is like this. So for the language models, what is the equivalent concept of such axioms underlying the field? And that's more like the most capable model at the time. And if anything, this changes. So say GPT-4 came out, and then researchers built on top of it, a lot of research experiments, intuitions built on top of it. And then later on, some better model comes out, then many of these ideas are outdated, in many cases contradictory. And it's really important to think about this. And this calls for the need to constantly unlearn the intuitions based on such invalidated ideas. And this is somewhat a new concept that I rarely see people practice. And I think this is, we have seen this very competitive field of AI. There are many cases where people with 1 or 2 years of experience come in and have very impactful ideas and work done. And I think some of that has to do with this newcomers just come in with the fresh perspective and then try out the ideas that experienced people have tried in the past that did not work with the model at the time. Now it suddenly works. This, I think, is a very neutralizing force. And for people experienced in the field, I think this is something to think about. Another perspective I would like to talk about is we should go ahead of the scaling curve. So here's what I mean. When I work on this day-to-day research, here's kind of the mental picture I have. Document all the experiments that fail and because of this insufficient intelligence. So this is a very vague term, but maybe it doesn't just have enough reasoning capability to solve this hard math problem or coding problem. Then I kind of just document it somewhere and do not declare failure yet and make it easy to rerun in the future. And as soon as the new, better model comes out, rerun them, and then learn what works and what doesn't. And with this, I update my intuition, unlearn necessary stuff, and really build the intuition around emergent abilities associated with the scale. I think this will become more and more important. So here's a visual way of thinking about this. Let's, again, very simplified, not all the tasks work like this, but the scale is just whatever, just some scale. And then I just put GPT-3 and 4 for the illustration purposes of 2 models at different scale. And let's think about this graph on the left, ability 1, some ability. And this one, GPT-4 cannot do it yet, but it's very close to the inflection point that a little bit better model, then we will probably suddenly see this jump. And then the ability in the middle, we have even this powerful GPT-4 model is so far away from it that any kind of like approach is probably not going to work in a meaningful sense. And ability 3 on the right, this is GPT-3 is even past the inflection point. And at this point, whatever I work on will probably be incremental changes. And that is kind of the implication. In reality, I cannot think of whatever problem that I'm solving falls under one or two, but just having this mental framework and always thinking about it and going back to the previous slide, updating my intuition really makes it easier to pin down which problem I'm solving. So that's kind of the perspective I want to introduce. So the summary is that everything we do has to do with scale, and scale first perspective is really critical. But how do we actually build the scaling? How do the scaling done in the field? So in the next 20 minutes or so, I'll think about this problem. And so far, all the large language models use this transformer architecture. You probably have seen this plot many, many times. The details don't really matter. For us, this talk, we will think about the fundamental ideas and then build up from first principles. And for that, we need to aggressively abstract out unnecessary details. For that, I would like to say the internals of the transformers don't really matter as much. And so we are going to take this functional viewpoint of the transformer and just think about it as a sequence-to-sequence mapping with a bunch of matmos, matrix multiplications, with the following array transformation. The input is a sequence with batch D model, which is kind of the width of the transformer, and length, the sequence length. And the output is same size array, and this is for training. For inference, it's different, but scaling happens at pre-training time, and that's this is the same length. So that's going to be the picture of the transform. Very simple sequence-to-sequence mapping. So let me illustrate with this functional viewpoint, input and the output shapes what happens from the beginning. So typically we have this sentence like this. I just took a random example. Many words don't map to one token, : indivisible. This is a string, so the shape of that is just string. And then the first step is to tokenize it. And then tokenization is done with some BPE or sentence piece, which is essentially an external model that try to compress the text as much as possible. So here we get the integer list. So now the shape is length. And then now we embed it into this hidden space, which we call, used to call word embedding. Now the representation of each token is its vector of size D model, and we have length of them. So shape is D model by length. And this is where actual computation happens. We have n transformer layers. And like I said, this is just a mapping from the same sequence to sequence. And here, everything is about scale, and scale really needs to be have as little assumption as possible. Here, what we want is each sequence token wants to interact with other tokens in the sequence. So we should just let them do it, but not get in the way of how they do it. So the one way of doing this in transformer is just let them able to take the dot product. That's it, and everything else is kind of details, and model learns to do which one to take the dot product and so on. So this is where major computation happens, and because it's a high dimensional array, we're talking about matrix multiplication or array computation. So at the end of this transformer, we get the sequence, and then we just take this loss function, which I'll cover in the later section. This is just a maximum likelihood based on next token prediction. So just predict the next token. And we get a single number. Now we do the backprop and update all the parameters and so on. In practice, we do it in batch, which only means we just have this batch dimension prepended at the shape. The only interdependence across the batch is at the end, when we take the loss, we take the average of that. That's all the process. And like I said, this is where vast majority of the compute is happening. And so when we say scaling the transformer, this is where we're scaling, and we need to understand this part in depth. So let's do that. From first principle, scaling transformer means doing that part very well, which means efficiently doing matmos with many, many machines. And this involves distributing or allocating all these matrices involved in the transformers to various machines. Which machine gets which part of the matrix, and so on. That allocation is the critical part, and we should do that while minimizing the communication between the machines. So this is the scaling perspective at the very low level. So that means we should think about this matrix multiplication. So I'm going to talk about this trivial matrix multiplication. Probably everyone knows how to do, but with the twist that we are using multiple machines and do it in a very scalable manner. We're going to scale it up to transformers later. So one at a time. So now let's say we have some 8 machines. There might be CPUs or GPUs. Now the first, and then we're going to do this trivial A, B equals to C, 16 by 16 matrix multiplication. And for that, the first step is to think about some kind of abstraction over hardware. These 8 GPUs or CPUs might be in the same room or same cluster, or maybe in different rooms or different buildings, whatever. We don't want to deal with such things. We define this mesh, which is like 2 by 4 grid, and then this layout is in virtual space. We don't care what the physical layout is. And we label this x-axis and then y-axis for this hardware mesh. And then the job is for every arrays involved in this computation, we map this array axis to the hardware axis. That's what we're going to do. And so here I use little color notation where this first row dimension of A is a red 16y, means this dimension is mapped to y, and then yellow x means that dimension is mapped to x. So because there are 2 machines across y-axis and 4 machines across x-axis, what that means is these rows are split into 2 ways, columns are 4 ways. So that's what I have this labels, machine 1, 2, 3, 4, and so on. This is the allocation for the matrices. Now, let's think about what machine 1 does. And it has to do, if you look at the C, the output matrix, we want to specify that after this matrix multiplication, we want the machine 1 to have this slice on the top left corner of 8 by 4. So that's a requirement. And then we see what it needs to do. So it has to do, if you think about this matrix multiplication, we do like column-wise and row-wise. And so it has to get some data. It doesn't have everything it needs to do this computation. So we do that with this all gather operation, which is one of the MPI operations. And we will look at this. So communicate with the 4 machines. So 1, 2, 3, 4, each having their local data. And then after, it talks to 2, 3, and 4, gets the data, and it has all the copies. And all of them does the same thing, which is why it's all gather instead of just gather. And that's the process that happens. After this, machine 1 has all the copies it needs to do that computation. And that's what happens. And crucially, this part is done in parallel across all 8 machines. And that's where the speed up comes up. And then the cost was that the communication has to happen. So that's kind of the trade-off between the two. We have to think about the speed up being larger than the communication cost. So that's the matrix multiplication. Let's generalize a little bit. MapMul, we can generalize to EINSUM, Einstein summation notation, which is just a higher level view of this array computation. So the 2 rules are if the letter appears in both input, multiply component-wise. I'll show you this. So if you look at the first one, numpy EINSUM of I, I becomes I. So we have both letter I appears in the input. That means we just multiply component-wise to get I. So this is equivalent to 8 times B in NumPy. And then if the letter doesn't appear on the output, then sum over that dimension. I, becoming nothing. So we should do that component-wise multiplication and then sum it over. And if the letter appears, and the third one is ij, j going to I. So what we do is just take the dot product over j, and then you get this comma. So that's the matrix vector multiplication, if you will. So that's the view of EINSUM. It can add many more dimensions. It doesn't have to be 2 or 1, it can be as many dimensions as possible. So now matrix multiplication from this perspective can be expressed as EINSUM of mn, mg, with m being this contracting dimension. We take the product, sum it over to get mp of AEB. So that's that. Why are we doing this? We go back to this matrix multiplication example with this EINSUM. So I put it here. And then now, because we all have labels for these array axes, mp, mn, whatever. So now this mapping means that I'm just saying n is array axis mapped to y hardware axis and mapped to x axis. And let's think about this, some magic decorator parallelize that has this mapping and does it for you. And I'm going to talk about how this might be actually implemented later, but the real implementation of some kind actually looks like this. So very similar to this. And we'll just think about it as a magic. So what it does is it inserts it all gathers in 2 dimensions and gives you back the parallelized version of this. So that's that. So EINSUM really exposes what we need to do. So yeah, now generalize one more thing. we were doing matmos, but we are interested in transformers. So the most complicated operation happening is the self-attention layer in the transformer, which can be represented in einsums. Everything except for the softmax can be expressed in einsum. So we don't have to go into details, but you can lay out like just cleanly like this, and you have some inputs, X being this sequence of three-dimension batch, the model by length, and then all these are model parameters that are learned and will be updated. So when you have this, you have a bunch of einsum operations with labeled array axes. Now, let's go to just parallelization of this thing. So we have 8 machines. Now, instead of calling it X or Y, by convention, we call it data and model. And that is data parallel dimension and model parallel dimension. We're doing both data and model parallelism. And this is kind of the mesh TensorFlow way, old in like 2018. But now it's a little bit more general, but we still use this terminology. So changing this code, very little change. We just put this parallelize and just put B is mapped to data, because B is like the batch dimension. We split across the machines in the data axis. And N is the sequence length. We never, in any transformer parallel version, we never parallelize across the sequence length because there are so many like things happening there. And D, nothing. H, the number of heads, is the model. Actually, this is why multi-head attention, the inventor is Noam Chazir, and he actually likes really parallelizing stuff. And so how can we parallelize this attention mechanism? If we split it into very separate heads, then you can do it. So that's actually motivated by this kind of a strategy. So now once you have this, you can use the exact same code and then just put it in, and you will get back this parallelized version that you can run with 8 machines or how many ever you want. So that has been toy example, 8 machines. But this exact framework actually works with any number of machines. And here I got it from the Google blog post. And this is actually what happens. So in TPU V4 pod, it can utilize like 3072 chips. And when we were training PaLM model, we used 2 pods. So it's like 6,000 chips showing here, each one being very as capable as some of the highest end GPUs. So now you have this bunch of machines. You define a mesh, still the same thing. Model parallel dimension is 48, and data parallel dimension is shown in 2D, but you can flatten it out, and then you have a 64. In PaLM, we actually use different things, but actually this is exactly same framework, just more machines. One last bit of detail is this DCN data parallelism. So when the 2 pods are really not connected in anything, but it's connected with the data center network, I think it's like 25 GPS per second. So this is slow compared to what's connecting the GPU pods. So here, we should not do any model parallelism. What we do is after the gradient computation, we sum the gradient over this data center network, and that's done only once, and that takes, say, 1 second or something. I don't know exact number, but this is fine because when we're training models like PaLM 540 billion, you can actually look at the paper. Each train step takes like 17 seconds. So if you add in like a 1 second here and there or 0.5, doesn't really matter. This is really different from small model training where we're thinking about steps per time. We're talking about seconds per step. So I think also it's really cool to just experience-wise, I type in some code and then enter in my laptop, and then it just runs on all these machines. That I think is really cool, and I think scaling, if you understand this, that what's happening at the end is just matrix multiplication with many machines that I just explained, you'll probably feel a lot better about this process. So far, we have assumed that this parallelized decorator just works. How is it actually done? One approach is this GSPMD. I linked the paper there, and it's a compiler-based approach. And you write neural net code as if you have a machine with infinite memory. So you don't really have to parallelize anything, which is kind of the approach we took. We just wrote no communication written, and then represent the core part of this neural net, say this train step as a computation graph. And then you can just, the graph is defined by some input tensor coming in, output array going out, and so on. You just specify how those are mapped to the hardware axis. It's the same process with it, and give that to XLA. it automatically inserts all gather any other communications that has to happen to use all that machine. And this is literally a magic when it works. It doesn't always work, and it really requires a lot of iterations, and many people struggle. Now I think it really works. And if you think about all the big models that came out of Google, T5, PaLM, Switch Transformer, all these things use GSPMD as a backend, exactly using the process I described. Other approaches exist. I'm not as familiar than this one, but you could think about manually annotating instead of doing the compiler, the operations. But at the end, the process is just the same. All involves mapping the array axes to hardwares. That's all. And manual approach is sometimes better because you have more control over. So I have some concrete examples. So this one is this process of doing GSPMD is too probably complicated for most researchers. So JAX exposes this front end called PJIT. I think now it's just called JIT because it just becomes a so useful thing. And just the process is we define this train step that has to be parallelized, and then we wrap this with JAX at PJIT, which is a decorator thing. You get back this partition train step that can run with many machines. And this exact code path actually was used to train PaLM. And so you can take a look how this kind of thing is actually done. It's a little bit more boilerplate, but now that you have this framework understanding, you can probably just have some ideas what's going on there. These codes are open source, and this is based on this T5X framework. We have very short paper illustrating the systems there. I linked it at the bottom there. So that's good. It's all about engineering hardware, system level thing. What about this machine learning picture? So here is a Llama 2 which recently came out. So all looks good after a successful run. But one critical thing when you're actually running pre-training is that it's really expensive to iterate on ideas. Maybe you want to do this kind of data split, or you want to do this. And each run has to be done at some scale, and that's really expensive. So this is the ideal picture. In reality, if you're running on this, so let's say this is a 2 trillion tokens, right? I don't know how long it took. So let's say it's 50 days. Then let's think about in one day what the progress looks like. It's like this. And you have to make decisions. Oh, looks like our 70 billion model is doing well. And that, I don't think I can make that call. And this is already using one day of thousands of GPUs hogged up. And then to do some experiment, this is very difficult. So, and this is even a good case. And sometimes it's not really clear what to do. And making decisions with this many resources waiting for me is just quite stressful situation. So this brings to the fundamental thing in pre-training is all about scaling laws, and GPT-4 technical report has some ideas about this, and OpenAI has published scaling laws paper in the past. That I think is really critical concept. So here we're talking about prediction, extrapolation of the performance of the pre-trained model across orders of magnitudes, just GPT-4, this one is a prediction. And this scaling law is developed with small scale model. So now we can see, okay, if we were to scale up, then this might be what we get. And we kind of, this is like the test loss on the unseen corpus, but this is the guiding principle. And so this picture is a lot more satisfactory if you have underlying scaling laws. And this is really the critical part of the pre-training. So I would like to say that now scaling is like a lot easier than say 2 years ago, but still very hard. And it's just not going from some flag small to large because of the mentioned reasons. And maybe one example, in PaLM training, there were like loss spikes. This is actually from the papers, you can check it out. There were about 20 loss spikes that happened. And this really unnerves many people, like just loss spiking up from like 2 to 6. It's really looks not good. So we trained 3 models, exact same data, but only one of them had the largest one. And so it's hard to debug and really hard to reproduce this kind of thing at smaller scale. And this is not caused by bad data. Some researchers run this experiments to verify this hypothesis. And then when this happens, every hour we not making the decision is like having this giant 6144 chips sitting idle, and that's really hard. And so this kind of makes really scaling challenging. And also, but then Llama 2 and all these things make much easier to train for a given size, like tens of billions of model like Llama, it's easier to train. But I would say that scale is increasing at a faster rate than the rate at which things become easier. At the frontier of the frontier, it's always challenging for many reasons. But most people will be not scaling up. I think you can just wait for them to do the hard work, get it, and do interesting research on top of it. So that leads to this next section. Scaling doesn't solve all the problems. We also need to do a lot more research on top of this massive engineering work. And many of those can be framed into this post-training. So let me talk about some motivations why we might need post-training. We cannot talk directly to this pre-trained model because the learning objective was just next token prediction. So here's one example I put. Let's say the input was make up a word that means when two AI researchers go on a date, and then pre-trained model will just continue generating because it doesn't know that it has to answer the question. It just predict whatever is the most likely and just go on forever. And whereas what we want is more like this, just crisp answer. And this is kind of the language models that we know how they behave. So that's one problem. This one, we have a remedy, more like a hack. We can frame the question so that the answer happens to be the next token. So here's another question, it's a square root, whatever, some question, and then we give a colon. And then the model just doing the next prediction, now it's like answering this question is probably the most natural thing, so we just do it. If it doesn't, then we can put an example, a few examples with the answer so that it knows how to do the thing. This is a few-shot prompting. It is quite powerful technique, but it's not really general and it's probably not the most principled solution. So probably a bigger problem than this formatting error is that pre-trained models always generate something that is natural continuation of the prompts, even if the prompts are malicious, harmful, and so on. And in particular, it doesn't know how to refuse a prompt. And all these capabilities that we think are important is taught at the post-training level. Sometimes people call it alignment to human values. I just call it post-training. Here, here's kind of the 4 stages of current generation of large language models. Pre-training is the first stage, and then there are 3 remaining stages: instruction fine-tuning, or sometimes people call it SFT, supervised fine-tuning, and then reward model and policy model training. That's kind of the RL part, RLHF. So we'll go in these 3 orders, 1, 2, 3. So let's take a look at the instruction fine-tuning. The high-level idea is that we frame all the tasks in the form of natural language instruction to natural language response mapping. So I think the best way to think about this is what we did before we had this idea. So if we go back to 2018, BERT was the best model at the time. And say we are solving this classification task. We just have, again, functional viewpoint. Input is the text, output is the label, classification label. To do this kind of task, we have to do BERT maps the sentence, and then you need to project to the classification space. We need a task-specific parameter. And this was not really fun to extend it out to multiple tasks. T5, a year after, came along with unification of the architectures, and that now the output is text. So you just map text to text. All the tasks look similar, same, and it's much better. But now if you're training on multiple tasks, multitask learning, then there's no way to distinguish the task. So you kind of put in this metadata. This is COLA task from Glue, and then some additional things for other tasks, so that at the inference time, if you prepend this, then the model knows that I'm solving this COLA task. But this is very unnatural. Instruction following goes one step further and explains the task in natural language. Is the following sentence acceptable? That's exactly what we mean by COLA task. We don't really need COLA. That's just some random data. And this is what we mean. And then explain the concept. And for the other task, we can also do the same thing, explain in natural language. The model understands and does the task. So this Now, looking back, this is so obvious we should have done this. Why this was not obvious at the time of T5 2019, 2018 was that at the time, people did not really think that language models understand the instruction. So having this kind of metadata felt more natural, and even this was like a stretch. So now we have larger models where kind of the emergence is this understanding, which in a very vague sense is possible. This kind of utilizing the rich space of natural language makes all the things unified. So that's the viewpoint of net instruction following. And maybe one more generalization will be instead of instruction in response out, you can think about dialogue as a kind of ultimate, most general form of two agents interacting, and some of them involve question answering or other things. So this is the instruction fine-tuning idea. So last year, when I was still at Google, I did we'd work on this paper where we pushed the limit of instruction fine-tuning. Okay, so instruction, actually, let me just take one more thing. So if you train on these instructions, say you see a new task at the inference time, then the task is unseen during training, but still, this is just framed as a instruction. So you just follow that instruction. That's how the generalization is done. And I think it's really critical concept. So that means if we have more instructions in the training set, would that be a better model, better generalization happening? And that was the hypothesis we tested with this massive thing, tasks. So at the time, we gathered pretty much all the academic tasks we could find. Then there were like 1,836 of them, put it into one mixture, train it. I won't go into detail. I linked this paper at the bottom. And this is where like Flan T5 and Flan Palm, those models came out. And so here we have a model X size and the x-axis. Whenever we think about some idea, always plot the scaling so that we understand the effect of the scale on this research idea. 8 billion, 62 billion, 540 billion. And on the y-axis, some average score of the evaluation set. We carefully picked 6 of them unseen during training and very hard, as evidenced by this 8 billion palm model, which was trained well, but still getting less than 10%. So the takeaway is that as we go from this gray line to the darker and darker blue, we add more tasks and the performance monotonically increases, but with the diminishing return. And that is more probably clearly shown in this plot on the right, number of fine-tuning tasks on the right, and then same data point, but you see like each model gets benefit of like 10%, but adding more tasks doesn't really help. So what matters is the task diversity. But still, even with this 1,800 tasks, massive benefits happen for any model size we have tried, any model family we have tried. And I think for this kind of method, it's hard to see any use cases that doesn't benefit from this. So very effective, but it has inherent limitations. Again, let's think about fundamental reasons why this might be not so scalable or effective. And for that, we need to go to the learning objective. In this learning phase, what are we teaching the model? And so learning objective, that is supervised learning with cross-entropy loss or maximum likelihood objective, which means for this given input, the target we have is the single correct answer, everything else is wrong. Very strong statement. In reinforcement learning literature, this is called the behavior cloning. I kind of like this terminology better. So the hope is that if we have enough of these variations, the model can generalize to different types, even though the training signal was quite prescriptive. So crucially, this requires formalizing the correct behavior for a given input so that the model can clone. And this has been easy and straightforward in the past. Increasingly, this is becoming more difficult. And the way I'm going to illustrate this is I'm going to show you a bunch of examples, and let's do a thought experiments where just think about the single correct answer. It has to be a single one. So start with the trivial example, 2 plus 3. Then it's obvious that the answer is 5. Maybe the answer is 5 might be a better one. But anyway, this one, not ambiguous. Another one, a little bit more ambiguity here. Translate this Korean. I should have studied instead of watching this movie. And this one, I translated myself. I know Korean, so this probably is correct. But this, I don't, yeah, but it's a single correct answer, but there might be some variations in it. Now, this is kind of the prompts that we're actually dealing with in large language models. Write a letter to a 5-year-old boy from Santa Claus explaining that Santa Claus is not real, convey gently so as not to break his heart. And this one, I cannot think of any good answer, let alone the best one that I will confidently give it to the model and say, this is a single correct answer. So this kind of thing, I'm less confident and comfortable using this maximum likelihood as the learning objective for the largest model we have. And that's maybe a little concocted. So let's think about some more practical use cases. This is actually one of the favorite prompts that I use whenever there's a new model comes out. Implement logistic regression with gradient descent in Python. And for this one, there's no clean answer, single answer for this. You might like functional programming style, you might like object-oriented style, or you might, within that, your style might be different, and all those might be valid. So is it okay to give one of the completion as the only correct answer? So let's make some observations. Increasingly, we want to teach models more abstract and ambiguous behaviors. And objective function of the instruction fine-tuning seems to become the bottleneck. I don't have hard evidence. In practice, this generalizes quite well. But if we think about, say, 1,000 times larger model than GPT-4, are we comfortable teaching the model with this very narrow signal? At least I'm not. So then can we use something, what is this maximum likelihood objective? If I give you a model prediction and a target, then there's a predefined mathematical function that computes this loss or objective function. So there's no learnable parameter. If this is the bottleneck, can we make this more expressive and actually learn it and parameterize it? And that's kind of the key idea for the RLHF. And RL provides one of many ways of doing this using this learned objective function. So in RL, we try to maximize this expected reward function shown here. Very general formulation. So let's think about, say, an agent playing chess. At the end of the game, if it wins the game, we give the reward of 1, reward of 0 otherwise. This is a valid function we call a reward, but there's no learnable parameters or anything. But we can actually use a model to formulate the rewards for more complicated situations, and we call that a reward model. So from this perspective, how do we actually do that? We know how to do supervised learning with neural net very well. So let's use neural net to represent that reward model. And that brings it to the next stage of reward model. So the core idea here is that for a given input, we give 2 completions, and humans provide the preference instead of saying which one is the best answer. Among these 2, this is better. The initial, this kind of thing doesn't really say why, but this is better. And human labels, this is how models learn what humans prefer. And this, crucially, the completion 2 in this case is preferred, but it doesn't have to be the best one. It's just better than the other one. Then the model can learn the axis of difference, and this is really critical behavior. And why is this? Why do we use comparison for things like this? 2 plus 3. The fact that 5 is better than 4 is probably not useful because there's a single correct answer. Why not use the supervised learning with maximum likelihood objective function? But for Santa Claus example like this, I can probably come up with 2 somewhat, just good completions, and then just say this one is better. And that might be better. So the core hypothesis is that it's easier to compare than to absolutely grade something. So mathematics of this, I will probably skip it, but we just model it. I'll go very quickly. 2 completions, yi and yj, and call probability pij is the probability that completion I is better than j. And we get that label from humans, and we model that probability as a difference in reward, more specifically log odds, but that's kind of the model from 1952. And this, we just rearrange it and maximize this probability because it's essentially a maximum likelihood. The reward model is trained with the maximum likelihood, just maximize this probability, but that's fine because it's going to be rich function providing the signal to the policy model. which is the final stage of this large language model. And here, the objective function is what we just learned, reward model with the parameter phi that is fixed after the initial RL. And you might this might remind you of the GAN formulation where you have this discriminative generator. Here, we were kind of fixing one part of it and just doing the other iteration. So for this, we bring some prompts, this policy model, which is typically initialized from the supervised instruction fine-tune checkpoint. You just generate some completions for that prompt, give it to the reward model, it gives back the score. And based on that, if it's low, then I know, okay, this is not good. If it's high, then okay, I will do more of these. So it's a trial and error formalization in mathematics. That's essentially the high-level idea. And because we want to maximize it with the gradient-based iterative method, we just take the gradient, hope to take the gradient, and that is done by some policy gradient algorithms like PPO or anything that should work. So that's the idea, iterate while satisfying this RM model. And in doing so, RM encodes human preference and then gives it to the policy model, learn through RL. That's the kind of the framework. In practice, many people don't like this. And I secretly hear people saying, oh, we should just get rid of the RLHF. And many people say that, not just like, I'm not talking about OpenAI in specific, but just many people in the field say that. So why is it? It's really hard to get this right. RL is just so tricky and it can go wrong. And one failure mode that is probably the most common I would like to explain is what's called reward hacking. So let's say the human labelers label this completions, like comparison pairs, that this is better with whatever they're thinking about. But it happens to be that, say, the preferred completions are all longer. Then this policy model can exploit this fact that, okay, if I just give something longer, then the reward model likes it. And increasingly, it just gives something like dumb but long. Then it can get better and better rewards. This reward model is happy, and human preference goes down. This divergence is what we call reward hacking, and so hard to control. I don't think there's a great answer to this at this point, open-ended research question. And this kind of thing is really a good problem to solve, because I don't think we have used this RLHF any way. Like, this is just scratching the surface. So yeah, that's the kind of the failure mode that is most common. And there are kind of many ways to do that, but I'll probably skip that for now. So even with this kind of a fundamental challenge that it's hard to use it, why should we keep studying RLHF? Here's just my take. Maximum likelihood is too strong of an inductive bias. And if we think about very strong inductive bias, it will be problematic if we have much larger scale. So GPT-4 probably fine, but 1,000 times GPT-4 or even larger, this I think will be problematic. So learning this objective function to relieve this bottleneck in the inductive bias in scaling is a different paradigm, and there's a lot of room for improvements. We have seen some success stories with RLHF model like ChatGPT, but I think it's just a beginning. Also, here's my just personal take. If something is so principled, we should just keep at it until it works. So I would like to summarize this kind of what I just said in the post-training section with bird's eye view of the field of AI progress, starting with this rule-based system, which I'm not really familiar with, so I might make mistakes, but just high-level concept matters here. Input is mapped by this hand-designed program to output, and here nothing is learned. And the next generation is like a classical machine learning system where input is transformed to hand-designed features, and then that gets mapped to an output by this learnable part that is, let's say, like an SVM or something. And this is the, I label learnable part with the blue box. And then the output is fed to along with the input, hand design loss function, objective function, and then iterate. So deep learning did change one thing. This is that hand design feature was changed to learn feature. In particular, hierarchical representation learning was the technique that defines deep learning. And this one change was really successful. And why is that? That is because it is a much weaker inductive bias, and that allows much more scalable system. and we have a lot more compute, utilize it, and that's how the deep learning success story can be summarized. So if we think about classical machine learning versus deep learning, the closest comparison will be logistic regression with the feed-forward neural net. Same thing, except for the fact that the representation, it has some hidden representation that is learned from the data, that is whatever the model thinks is a good thing to solve this binary classification test. So at this point, I was wondering what will be the next generation. If just changing, coloring one box with blue was so successful, why not do another thing? And I only see one box left over, which is this loss function. So this still is hand design. So maybe we should relieve that assumption and learn it. And that, I think, is the next generation. We have one or two success stories, GAN and RLHF. And this is, I think, really powerful. And it allows a model that demonstrates behaviors that is so hard to think about if you have to formalize the correct behavior. So, but it can be RLHF just one instance. It can be any other RL formulations or any types of other methods, not just RL. So that, I think, is the next paradigm, and we should go for that. And if I have to think about this mental picture, what is kind of the representative flagship model from each paradigm? Maybe like IBM, Deep Blue. I don't know what exactly uses, like some search with that, but let's call it just robust system. And then I don't actually have a good idea of any famous classical machine learning system. Let's call it some SVM-based ones. And then from there to the next paradigm was GPT-3. So now this much change happens in every paradigm. And I believe that learning this loss function or objective function is as big of a change from the previous steps. Then I think it's really exciting to think about what can come out of this. That's it. Thank you.
Well, thank you very much, Dr. Zhang. It's a lot of information in a short time, so it's hard to digest all. But it's really comprehensive coverage of these language models. So now, please, audience, please ask questions to Dr. Zhang or provide some comment. Philip Cabrera. Please go ahead. Yeah.
Yes. Can you hear me?
Yeah. Can you show your face?
Unfortunately, my camera is broken at this notebook.
Okay. Go ahead. We should provide you a notebook.
I can organize a webcam for the next lecture. So
okay, go ahead.
First of all, thanks a lot for this interesting talk. As you now talked a bit about the future as you could imagine it, like having a learned loss function instead of a hand-designed one, I was also wondering if you could imagine a potential shift from those large language models being only focusing on predicting the next token to maybe encoding the overall output so that we might get also rid of hallucination problems and so on. Like I imagine it a bit into the direction of stable diffusion. But of course, for stable diffusion, we have the benefit that we know the output size in terms of pixel width and height. But could you imagine adapting language models in such a stable way so that we are not biased towards generating one token after another until we have hallucination?
Yeah, so I think that's a very open-ended question. So maybe I will unpack this. Hallucination, we don't really understand why it's happening. I think one possibility is, let's think about, instead of hallucination, something that is hard to measure, think about calibration, whether the model is calibrated or not. And if you think about the training, next token prediction, the key feature is that it's teacher forced, right? The output of this time step doesn't really affect anything about the next time step input. So the errors don't really propagate forward. So here is kind of a fixing mechanism. We, every time you have this like a probability measure that is kind of calibrated, the model really is calibrated. So if you look at GPT-4 technical report, we have this like a plot where GPT-4 pre-trained model is actually calibrated according to one measure, but the PPO, the RL model, is not. My take is that I don't know if this is like a correct or not, but my intuition is that RL is different in that it's more like a sequence level signal, as you suggested, right? Model generates the whole thing while propagating the errors and then get one signal out of it. So I think the calibration might be broken there. Whether calibration is necessary to not hallucinate, I don't know the answer. And I think many people differ in this thing, but it's probably good to have some calibration in there. I think some RL signal, actually, if you look at there's might be a way to do RL where some of the learning signals is directly calibrating it and see if calibration can fix this hallucination. But yeah, I think that's something to be thought of. So I think the key point is that what is the artifacts of pre-training objectives? It's teacher forcing, and it has been really effective. And I'm a little bit concerned because pre-training length, the sequence length is getting longer and longer. So maybe at like 500 tokens is fine to teacher force it. But if we do like, I don't know, 100K, just making up numbers, does it really break up some fundamental capabilities of the model and it's not scalable? I don't know the answer, but I think it's really good to think about that.
All right. Thanks a lot for the answer.
Okay, Juyong Choi.
Thank you for the extensive talk. So as a deep learning researcher,
Can you introduce yourself?
I am a PhD student at mathematical science in Seoul National University. I am currently studying deep learning, and as a deep learning researcher, I have a desire to study LLM. However, as you know, like unlike very large corporation, OpenAI or Google, most research lab does not have computational budget to freely study the LLM. So is there any like aspect of research or advice that you can give to those graduate students or small labs for studying LLMs?
Yeah, I think it's really hard question. I get it a lot of times and I don't have a good answer, but let me try. I think or at least some guiding principles. I think first of all, what should you not do? I think you should not compete with the scale, like problem solving the research directions that some larger model can just solve is not really a good idea. And then probably better to think about some problems that don't benefit from scale. And I think hallucination or this calibration might fall into that. Like if you think about 1,000 times larger GPT-4 just comes out and then it doesn't hallucinate, I think that'll be probably difficult. So something about this learning inductive biases that we put into the system that doesn't address this. So that kind of thing is really necessary. And this probably can be studied at a much smaller scale. But again, I would do a lot of the scaling studies initially so that whatever you do at scale, finding the smallest scale that's still signal bearing at a larger scale is something that I recommend to a lot of people. And also, I think I mentioned this, most people don't actually work on scaling. And if you think about like ChatGPT UI, like it's one of the versions is like free, like it's not the best one, but so I think you can do a lot with that. And if you can like predict what will be the emergent behaviors of the next one and kind of figure out what are the limitations of this model and set out a lot of the experiments to really figure out that. And then some company releases the better model, you try out their ideas and then find out that it works. I think that could be really a way to leverage the current trend where people are doing the work for you. Scaling is really hard, but another way of doing it is like they just do the work for you and you think about how to leverage it as much as possible. It's all just optimistic view. I know I actually don't have any experience not having a lot of the compute, but I would just think about like, just from these perspectives. But that's kind of the best answer I could give.
Thank you.
Next is Jonghyun Choi.
Yes, hi, my name is Jonghyun Choi, and I'm an undergraduate student majoring in computer science at Seoul National University. I previously worked as a backend engineer at a company after taking 2 years off. And the question I wanted to ask was, I'm interested pursuing a career about scaling AI models and managing them to be more efficient and result in less cost. I believe there's such positions after AI models have become very hot topics for past 2 to 3 years. But I think the career path for this kind of position is still very kind of vague, and the information is not that public. And I want to ask you, which learning area should I focus or build experience to recommend? Do you recommend to best prepare for such career path?
Sorry if I understand the question correctly. You're asking about the career path, and the career you're interested in is like a kind of this scale engineering, more on the serving side to make it efficient, or training side, or what was the? Can you repeat the question? On the sorry.
On the serving side.
Oh, on the serving side. Yeah, I mean similar kind of logics happens. Like I don't know if you have seen this paper on PaLM optimize inference that came out. That paper has this like some of the best system engineers at Google doing their incredible work. And I have a really big respect for every author on that paper. And that I think is kind of the thing you want if you like understanding the fundamentals of this. And many of the talks I have given, training and serving, not that different. If you at the fundamental level, training and serving are majorly different by that, you have to do teacher forcing, so you don't really care about the parameter transfer between the model happens only twice for backward pass. For serving, it happens every time step. So that communication cost characteristic is completely different. But other than that, all this communication versus parallelization trade-off requires similar types of knowledge. And so I don't think it's a different career path. In terms of how to get there, I think such knowledge and people with such knowledge was really, really critical. I think more people have this now, but back in, say, when we're training PaLM, there are only like small number of people who are always busy because they're just so critical. And that requires system level engineering on this, like compiler or kernels, and these things I think will probably be really useful. And what do you need to do that? I recommend not getting directly into those, and this just my take. I think getting the fundamental is a lot more important. Why? Because 3 years from now, who knows what will be the most important skill set. Like I have even seen that when we were training PaLM, the skill set that were required is very different from what is necessary now. So I would focus on what is still relevant and what will be the still relevant thing. And that's like fundamental understanding for this system, like computer systems and just very basics like hardware and software co-design and things like that. I would study all those things before jumping into actual product, or actually do it in parallel, but do not jump right into the most fancy stuff. And that will be kind of the fundamental stuff. So yeah, and I'm not an expert in that area. So in terms of what material, I don't know, but that will be the kind of the material. Did that answer your question?
Oh, yes. Thank you for the explanation.
I think there are a lot of questions are coming up, but now I would like to hand over to Professor Keun-Kwan Yu, who turned on screened. Professor Yu, do you have a comment or questions?
Dr. Chung, I appreciate your impressive talk, but I have to admit that I have very limited understanding of what you have said. Still, I have two quick questions. First, let's compare training large language model to child raising of young parents. So regarding the emergence phenomena and regarding the perspective of yet principle, some young parents might think that their kid is a genius. So the parents take the kid to the swimming pool, to the tennis court, sometimes to mass tutoring class. In many cases, after a certain period of time, they can float on water. After a certain period of time, they can hit forehand. But in other tests, they would never achieve any meaningful level of performance. So my question is, how do we know whether it's yet or never? That's my first question. The second question is, if it's supervised learning, the task is easier. But if it's reinforcement learning, as you pointed out several times, objective is important. But if we compare large language model to human being, then each different human being has different objective, different purpose, different criteria. Some people would like to optimize, other people would simply want to compromise. So some kind of dialogue between AI experts and the evolutionary biologists, I think would be mutually beneficial. How do you think about this second part as well? Thank you.
Okay, so I don't think I have a good answer for either of those. I don't really, but here's my take. So I personally don't try to map this computer learning to human learning. I think these are very different entities, and we don't really have to build like humans, especially if you're thinking about building ASI, super intelligence, that is probably better than, more smart than humans. I don't think we should just wait for, like, just copy humans. And also, these have a very different characteristics. Like, it can just consume a lot of the data and a lot of compute, which goes up by a lot. And so I think I kind of think about just decouple that completely. But even then, maybe if I stretch a lot, some abilities, like which one will emerge or not, I think it's more of a time scale. If I take the most like scaling maximalist approach, if you say like some ability might not emerge, then I'll say add more zeros and until it appears. At some point, I think it's possible to do such tasks, and if it's cognitive. And so, yeah, that will be my guess. And in terms of like child learning, I think some analogies might be like pre-training might be more closer to like evolution. So if, say, some child never learns to fly, most people don't, right? No one does. But if we have evolved more training and that was useful for survival, maybe that was possible. That's what I'm saying, like by unlikely, but just adding a lot more zeros, I think it's many things are possible. On the second part, here, the question is like, if I rephrase it, correct me if I'm wrong. So we are teaching human preference, but everyone has a different value. How do we teach the right thing, and who decides that? Is that a good framing of this question?
Yes.
Yeah, I think it's like an ongoing discussion. And one approach that seems promising is this Anthropic's constitutional AI. So here, instead of defining, like, this means like who labels this preference defines the model's behavior collectively. But what if AI does that? AI who follows instructions and follows these constitutions that people collectively agree upon, say some like hundreds of constitutions, and then all the preferences based on following those, then I think that's more tractable problem than individually participating in this labeling. So I think this is still very early work. And so, yeah, that I think seems like a more feasible approach. Some discussions going on internally. I don't think I can share all that, but yeah, this is a very important problem that people are actively working on. And that's just my favorite take, this constitution. And whether we agree or not, probably some kind of a governing body, maybe an international one, I don't know, but agree on this constitutions. And then methodology wise, we just let impartial entity like AI encodes that into preference labeling if we still do RLHF at the time.
Thank you.
Next, 손성우.
Hi, thank you so much for the extensive talk. And hi, I am a first-year PhD student majoring in data science and SNU. One part that I've been curious about is the not yet part of the slides. In the perspective of the capability of the models currently, current large models and like not not confining just towards the large language model, but large models in general seems to already be able to like process videos and images, and it seems like it's like doing the entire multimodality part of it. And so one thing that I've been most curious was what, like, is there as a next step, like do you see like the models doing additional different capabilities besides what we currently see?
Yeah. So I think this is where I was trying to avoid, but I probably have to do it, like predicting what will be the emergent abilities. So here, I mean, with my friends at OpenAI, we just kind of predict this all the time. And my take, I think your question is like, what will be the what will be the ability that are like ability 1 here? Is that the right question?
Yeah, that's correct.
Yeah. So my vote is that this self-reflection is kind of the ability that barely starts seeing in GPT-4, and meaning like it's evaluating the output of the output from similar model, like with different prompts, but still like same model family. That seems to be feasible, and that's happening with like evaluating the output with the model. That seems probably like very doable. And then decision making has to use this self-reflection, right? You just think about what you just generated and then go from there. This doesn't really work well, but it was impossible for any previous generation. I think we have some signal. And where is this used? I think this is the agents. What I think the bottleneck is just self-reflection. And if I have to bet, we are probably closer to some aspects of that. Maybe not all the way. We still need to go up in this linear region, but I think that will probably be the most exciting emergent abilities I will bet on. Yeah, that's it.
So yeah,
Thank
we
you
have
so
two
much.
more questions to go. Dr. Jung, to Jo Min-gyu, can you make it short?
Hello, this is Mingyu, and I'm SNU alumni, and I'm currently working for a company named Mathpresso or Quanda. The company is providing the mathematical solutions and the explanation to the students worldwide. And obviously, we are very interested in solving mathematical problems using the language models. And we are wondering if the capability of reasoning power of language models. So if we increase the size of the language model and provide the adequate post-training and RLFF, reinforcement with human feedback, is that enough? Or do you think we may need to provide some kind of formalization using something like the lean, the proof assistant or something to get the correct answers of mathematical or some STEM problems?
Yeah, I think for my take is I'm very like scaling maximalist. So I think reasoning is, I mean, again, we need to define what reasoning is, but in a very, very vague sense, reasoning is something that really benefits from the scale. It's really hard to close the gap with all the techniques at the post-training stage between, say, GPT 3.5 and 4. They differ in the pre-training, and that difference in like the harder the problem, that's not something that we can close. And I'm expecting this trend will probably continue, and because previous model difference is getting larger, if any, small data point, but I think it's plausible. So at this point, if I'm working on math problem, I'll probably not think about that. But RL of some signal that is directly relevant for math probably is useful, but it has to be scaled. And I think that is really interesting. I actually worked on some reasoning problems, but prompting and whatnot, but it's really hard. And I think just the problem definition itself is so unclear. So I think that's the best way for now is just waiting for the next big model, and that will probably be more effective than spending some time on unscalable approaches. It could be very long, but this is my take.
Thank you. I think we should collect the consulting fee from Quanda. No, I'm joking. Yeah. So I should call you guys. Next is Jehu, Anjehu.
Oh, hi, I'm Jae An, a second-year PhD student studying NLP in computer science department. Since you're in the cutting-edge AI company, I would like to ask the next step of GPT-4 and current LLM, which is orthogonal to merely scaling the model size. So as you know, the LLMs are vulnerable to kind of hallucination or factuality issue. And furthermore, they are different from humans in that they don't know what they're talking about usually, or even they're indeed creative or not. So I wonder what would be the next mission of the LLM overall. So this could be the main issue of the GPT-5, which is irrelevant to the scaling issue. And that was the first question. And the second was just a personal question. And I was just curious about the difference between working at OpenAI and versus working at Google research. Thank you.
Okay.
That's the question that I was thinking about. So thank you for asking instead of me. Yeah.
Yeah. So first question, I think I still think scaling is just model size compute, but also RL can be one of the ways. RL is a very end-to-end signal, and that requires some certain scale of training. So I would refer to this John Schulman's co-founder of OpenAI's talk at Berkeley. He talked about one way of using RL to essentially improve this factuality or hallucination problem. The core idea is that you just give, like for very wrong or incorrect answer, you just penalize accordingly. There's some RL signals there, and then that might be one way to do it. Like confident and wrong, and is like worse than hedging, and which is worse than getting the right answer. And I think if we have enough of a RL signal there, this can point to the much more factual model. And if we think about the current landscape, there's no direct signals like that, and it's very implicit. So I don't think it's something that we cannot solve. But yeah, I think it's really a difficult problem, but I am always thinking about RL signal. What I'm not gonna do is on this factuality front is some task specific parameter or some little tricks that may not be relevant in a couple of years. So end to end, I think RL with some direct penalization of non-factual, whatever you define that way, is I think that could be the one of the approaches. Second question, I think is probably hard to answer in like meaningful way, but let me try. I think culture-wise, I think is very similar in the sense that we work on similar things. OpenAI is like very much mission-driven. This is very cliche, but this actually is a defining feature. So everyone believes in AGI, and maybe some people don't believe in AGI when they get in, but it's hard to not be convinced of the AGI, how near it is. And that, if you think about Google, like 2022, mid 2022, no one but one person was using AGI. It was kind of cringy to even use that term, but I think that's so everyone was interested in deep learning, understanding deep learning. Google Brain was about deep learning and all those things, but not for specific things. So here's my mental picture: vector field. Everyone is a vector, and then they have many strong people, so strong magnitude. But they're in a very high dimensional space. They're pointing in a very different directions. OpenAI, I think, is like at the very high end. They are all pointing to AGI. I think this is really strong, and it's so easy to think about just same topic. And if I think about the lunch conversation at Google, it's a lot more diverse. Here, everything is about AI, AGI, and just so focused. And I think this really changes how I think about it. And I was very much of a scaling maximalist. When I arrived, I realized that I was not even a strong believer of this. So yeah, I think this comes down from the leadership, and leadership is a lot more hands-on. They have a very clear picture, and I think that's just how this mission-driven culture is built. So I think that's kind of the difference, and maybe we don't publish as much, and just building AGI is probably the main thing. But here's just my take. I mean, still people publish like InstructGPT paper. I think that the publication of that was like critical, and I think and some papers come out in OpenAI, and I think the hope it stays like that.
So, well, what's the number of the courses that you were on recently from OpenAI?
You with just GPT-4?
Yeah.
I don't know. I think it's over 100, maybe less than 200.
Okay.
But
Okay.
yeah.
Okay. Yeah. Okay. Yeah. I was just curious. Now, I think we have to cut down the questions. So if you want to ask a question, please make it very short. Chae-Suyong, yeah.
Thank you. Thank you for the meaningful lecture. I'm a master's student in computer science and engineering, researching artificial intelligence. Quick question. As you know, the transformer architecture has been used as a de facto model for years. What do you think about the possibility of developing an architecture with less inductive bias?
I think so. I'm very biased at this point. The architecture doesn't seem to be the bottleneck. So maybe some better architecture might be there. But if it's not a bottleneck, I don't think it's the most useful like investment. And it will change if we, like I said, I think the learning objective is probably the bottleneck if I have to pick one. And then it changes over time, right? So at some point, architecture might not be feasible for the new set of learning objectives, but probably it doesn't really matter that much. And based on my, actually, I might have some slides there. I actually worked on some paper where we did this transformer architectures on many different things, many different variations. And so in mesh TensorFlow, I give up on finding this, but we did 57 different variants of transformers and then tried on a bunch of things, and essentially nothing really worked. So, and if we scale it up, actually the difference goes away or even becomes negative. So, and if we have to think about what inductive bias do I want to put away from this transformer, I'm not sure if there's like a meaningful thing. I think I mentioned this when this is a sequence model, and the way we do sequence modeling is just by letting the model take the dot product of the token representations. I think that's quite general. So maybe, not sure, but multimodality maybe introduces a lot of different challenges because not everything is sequenced. So there, I think the architecture of the transformer might be too limiting. But this, at least for text, I think this is probably reasonably good.
Thank you for a great answer.
The last question, Chae-Suyong, you have a question?
No, thank you.
I think this
okay.
Is,
Seungju, okay.
And thank you for your great talk. And I really enjoyed the part about unlearning. Yeah, so my question is, how do you think about multimodal learning beyond just understanding images or other modal signals, but about the perspective of emergent abilities? So my take about the next step of large language models is to leverage multimodal signals from real world, because text-based data can provide limited amount of knowledge about the world. So yeah, I just want to know about your perspective or other people in OpenAI about this kind of multimodal learning or this stuff.
Yeah, I think probably I cannot think of anyone who doesn't agree that multimodality is like the next direction. And I have to say that I'm not an expert in that direction at all. So whatever I say is probably not really meaningful. But if I just reason from first principles, I think I don't have any clear evidence that if we put two different modalities, say image and text in the pre-training, they help each other. This kind of reminds me at this current scale, and that probably is the emergent internal ability. So this reminds me of this multilinguality research that I've done. So multilingual pre-training used to be thought of as, okay, 100 languages competing for the given capacity. And this was called like curse of multilinguality or something. And that was really the case. But now, if anything, putting more languages is probably better. They help, model has enough capacity. Suddenly this kind of fighting effect is more like cooperation. And the languages you only exist in English, you can ask in other languages and it actually gets transferred. So semantic level cross-lingual transfer is happening. I've seen many, many times. So languages are very similar, but modalities, images, and this without direct linking signal, I think that might be the next emergent abilities. Probably a lot more difficult, but I don't think it's impossible, and that will be really cool to unlock. Did that answer your question?
Oh yeah, thank you.
Well, Dr. Jung, I think thanks a lot for the really great talk and great answering. And I actually have two questions, but I don't want you answer in a long, just short. We are actually just increasing the scale at the moment, but increasing the scale takes a lot of computation. And what about splitting these big models into the smaller ones and make each smaller ones become an agent and let this agent talk to each other? What do you think about? What are the limitations you see when you move to this direction? And that's the first question. The second question is you transformed yourself from mechanical engineering, PhD to this, LLM specialist in just 4 years. How could this happen? That means that you don't have to spend 4 years training PhD students. Maybe 3 years, 2 or 3 years is good enough. I mean, you're an exception, maybe.
Yeah.
So that's the second question.
Sure. Okay. First question. I think my strong take that not many people like is that I think using smaller agents is probably not the best way because of this emergent abilities. When we think about agents talking to each other, understanding other models' output is probably as similar as understanding its own output, which is not even possible very well with GPT-4 scale. So if anything, you need a bigger scale. And I would even do larger model doing smaller amount of inference with just doing the agents. It can be its own thing. I think putting different prompts kind of makes the distribution different. So I think that might be the better way. So smaller agents is a very difficult problem. I think I should use the most capable model, if anything. That will be my guess. But the picture might be different. Second question is, I mean, I just got lucky in many, many ways, and that's probably the biggest factor. But also, as I alluded bit earlier, somewhere probably here, I think I just come up with stupid ideas that did not work, and some of that really worked out. And this kind of thing was really good. And I had, I think my approach was that I just learned the fundamentals. And also, I think the useful thing is many people have, say, PhD in machine learning, they have learned many special knowledge, but it's so sad that they get just outdated so fast. But then you put so much effort in it, so it's hard to just drop it. For me, I dropped PhD completely. Then I'm a lot freer to drop anything and work on whatever is the most impactful direction at the time, which is mostly the new thing, and no one is expert. So I'm not really competing with someone who has experience over 20 years. Everyone, for example, no one is experienced in prompting more than, say, 3 years, 3-4 years. That kind of thing is just everyone's kind of level ground, and whoever picks up faster is what matters the most. And I think I learned how to do that in PhD. It was about learning to learn, and I'm very excited about just learning, and that I think is probably one reason too. most important reason.
That is a great piece of advice to student and maybe faculty too. Thank you very much. I think
Thanks.
now we already passed the time that we set. I really appreciate Dr. Chung for this initiating this semester's with a great talk and a great discussion. So I look forward to seeing you more often in the Silicon Valley. And
Yeah.
well, thank you very much again.
Yeah,
Bye-bye.
thanks so much for having me.
Yeah, no. Let's give a big applause. Maybe people don't know. Yeah.
Thanks.
Okay, thank you. Yeah.
Yeah,
I'll
thanks.
call you
Bye.
soon. Yeah.